The weak formulation. You probably stumbled over this term already in one of your classes on finite elements or partial differential equations. And perhaps you had problems understanding where the weak formulation comes from and why it is so useful. In this video, we will take a close look at the weak formulation and visually explore its properties. If you never heard about the weak formulation before, don't worry, we will start from the very beginning here. Many problems in physics or engineering can be described by differential equations, which we want to solve for an unknown solution function. Here you see a differential equation in its conventional form, which is called the strong form. We will see later why. Transforming differential equations from their conventional form into what is called their weak form is nowadays an indispensable tool when it comes to numerically solving differential equations. However, just from looking at the formulas, it is not quite easy to understand the concept of the weak formulation. Why are there other functions than our unknown solution function in the weak formulation? What does it mean that the weak formulation has to hold true for all of these functions? And why is it even called weak formulation? These questions will be addressed in this video, and we will explore why the weak formulation is so incredibly useful for solving differential equations with the finite element method. And I promise you, once having understood the weak formulation, understanding the finite element method will be comparatively easy. But let's start from the very beginning. Before we talk about the weak formulation, let's take a look at the differential equation in its conventional form, the strong formulation. In this video, we will take a look at the arguably most popular differential equation, the Poisson equation. This differential equation is so popular because it naturally appears in many scientific applications. The strong formulation of the Poisson problem in 1D states that for a given function f of x, find a function u of x such that its second derivative, which is here denoted by u double prime, is equal to f of x. So we want to find a function u whose second derivative is f. Typically, we are only interested in how this function looks like on a specific region of interest. Here I'm choosing the interval from x equal to 0 to x equal to 1. Let's visualize this. We are interested in the function u of x. How this function looks like is not known. Here I'm just illustrating an exemplary function. As you know, the derivative of u describes the slope of u at each point x. And the second derivative, which appears in our differential equation, describes the slope of u, which can also be interpreted as the curvature of u. We have given a function f of x. In this video, I will assume that f of x is constant, taking the same value at each point x. I will denote this value by f bar. Our differential equation states that we want to find the function u such that its second derivative is equal to f. Here I'm illustrating an exemplary function whose second derivative equals f. So this function is a solution to our differential equation. Notice, however, that moving the function u up and down has no influence on the slope and no influence on the curvature of u. Likewise, rotating u does change the slope of u, but again it does not have an influence on the curvature of u. Therefore, we could find infinitely many functions u that fulfill our given differential equation. To avoid this, we add boundary conditions to our problem. Here I will assume that u at x equals 0 is 0 and the first derivative of u at x equals 1 is 0. There is only one function that fulfills the differential equation and the boundary conditions at the same time. For this very simple one-dimensional example, we can even find an analytical expression for this function. We obtain this quadratic expression for u. By plotting u and its derivatives, we observe that u indeed fulfills the differential equation because the second derivative of u equals f, and u indeed fulfills the boundary conditions because u is 0 at x equals 0 and u prime is 0 at x equals 1. Note, however, that deriving such analytical expressions for our solution is only possible for very simple differential equations. In general, the solution to the differential equation may not be so easy to compute by hand, and we have to rely on computer algorithms for finding the solution function u or sufficiently good approximations of it. The so-called finite element method is one of the most popular methods for solving differential equations numerically. The idea of the finite element method is to split our region of interest into a number of segments. These segments are called elements, and the points between the segments are called nodes. Next, we formulate a set of very simple functions, which are respectively 1 at one node and 0 at the other nodes. These functions are called shape functions. As we have 6 nodes in this example, there are 6 shape functions, which are denoted by n, and the index of n indicates to which node a shape function belongs to. Finally, we assume that our solution function can be expressed as the sum of the shape functions multiplied by a set of parameters, which are here denoted by ui. These parameters can take arbitrary values. If we set all of them to 0, our solution function is 0. By tweaking the parameters, we obtain differently shaped functions u. Note that, by assuming that our solution can be expressed as the sum of simple functions multiplied by tunable parameters, that is, by introducing a parametric ansatz for our solution, we have reformulated the problem of finding an unknown function into a problem of finding a set of unknown parameters. Such problems can be handled much better by computers. But how could we possibly find out which values the unknown parameters should take? The naive approach would be to substitute our assumed expression for the solution function into the differential equation and see if we can solve for the unknown parameters. But there is a catch. This naive strategy is not possible, which becomes clear immediately after looking at how the second derivative of our solution function looks like. Ignoring the points at which our function is not differentiable, we see that the second derivative of u is 0 everywhere. And this does not change upon changing the values of the unknown parameters. This means that there is no possible combination of parameters such that the strong formulation of the differential equation is fulfilled. We arrived at a dead end. We have introduced a parametric ansatz for our solution function, but we cannot substitute it in the differential equation to compute the unknown parameters in our ansatz. Therefore, we need to reformulate our problem into a form that is more suitable to be solved with the finite element method. We need to transform the strong formulation into what is called the weak formulation of the problem. So let's talk about the weak formulation. In what follows, we will derive the weak formulation from the strong formulation. And for the next few minutes, please do not focus on why we are doing this, but rather focus on why we are mathematically allowed to reformulate the problem like this. The usefulness of the weak formulation will become apparent later. First, we write down the problem in the strong form. Next, we introduce a type of functions which we call test functions v of x. The test functions are, like u of x, defined on an interval between x equals 0 and 1. And they may take any arbitrary shape on this interval. Now we multiply both sides of the differential equation by these test functions. This is a valid mathematical operation because we apply the same manipulations on both sides of the differential equation. If u double prime is equal to f, then also u double prime times v must be equal to f times v. Afterwards, we integrate both sides of the differential equation over our region of interest, that is from x equals 0 to x equals 1. Once again, this is a valid mathematical operation because we are applying the same manipulations on both sides of the equation. Note now that we can apply these manipulations on both sides of the differential equation for any arbitrarily chosen test function v. No matter how we choose v, our newly derived integral equation must hold true. Therefore, we write that the integral equation must hold true for all test functions v. Finally, like the strong formulation, the weak formulation must fulfill the boundary conditions. That's it. We have derived the weak formulation from the strong formulation by multiplying both sides of the differential equation by the test functions and integrating both sides of the equation over the region of interest. However, are we really allowed to do this? Whenever we manipulate an equation, we must be very careful not to lose any information that the equation provides us. So the natural question that arises is whether we can recover all information that the strong form provides us from the weak form. In other words, we know that we can derive the weak form from the strong form, but can we likewise derive the strong from the weak form? In the following, we will try to answer this question by visually exploring the weak formulation. Let's take a look at the weak formulation. And let's focus on the right-hand side of the equation first. The function f of x is given. We have assumed that it takes a constant value f bar. The test function v of x is arbitrary. The weak formulation must hold true for all test functions that we could think of. So we can choose any shape for the test function here. But let's choose a test function with a constant value of 1 for now. Next, let's plot f times v. Multiplying two functions is a pointwise operation. That means, for every point x, we multiply the corresponding values f of x and v of x. As f is constantly taking the value f bar and v is constantly 1, f times v is again a constant function that takes the value f bar. Note that the right-hand side of the weak form is the integral of f times v from 0 to 1, which describes this area here. Now let's move on to the left-hand side of our equation. The second derivative of u is unknown, because u is our unknown. The test function is the same as on the right-hand side of the equation, which we have arbitrarily chosen as constantly 1 for now. Finally, the second derivative of u times the test function v is also unknown because the second derivative of u is unknown. So the second derivative of u times the test function v can be a function of arbitrary shape. However, there is one constraint. The weak formulation tells us that the integral of u double prime times v must be equal to the integral of f times v. Therefore, this area must be equal to this area. This means that u double prime times v can take arbitrary shapes as long as the area is preserved. For example, this shape is allowed, or this shape, or this shape. Knowing that the integral of u double prime times v must be equal to the integral of f times v, what does this tell us about u double prime? In this particular example, we have chosen a test function that is constantly 1. This means that u double prime is equal to u double prime times v. But we can see that choosing the test function as constant does not provide us much information about how u double prime looks like. U double prime can take any shape as long as the integral of u double prime times v is equal to the integral of f times v. We can conclude that by choosing a test function of constantly 1, we force the integral of u double prime to be equal to the integral of f. However, we don't obtain any further information about how u double prime should look like. But the weak formulation must hold true for any test function. So let's see if we can construct a test function that is more useful for getting information about how u double prime looks like. Let's start with a test function that is 1 over an interval I and 0 elsewhere. F times v is now a function that is equal to f bar over this interval I and 0 elsewhere. We also know that u double prime times v must be 0 outside the interval I, because v is 0 there. Inside the interval, the shape of u double prime times v is unknown. We only know that its integral is equal to the integral of f times v. Because v is constantly 1 over the interval I, we know that u double prime and u double prime times v are equal over the interval I. But we do not know how u double prime could look like outside the interval I. On the first glance, it seems that we did not gain any new information about how u double prime should look like after changing the shape of our test function. But let's take a closer look. If we assume that u double prime is a continuous function, which we will do here, we can observe that u double prime must cross at some point in the interval I the value f bar. Even if we change the shape of u double prime crosses f bar at least once. This is because otherwise the area under u double prime times v cannot be equal to the area under f times v. Now, this is a useful information. We have chosen the test function v such that we know that u double prime takes the value f bar somewhere in the interval I. We just don't know where exactly. But let me remind you once more. The weak formulation must hold true for any test function. Therefore, we can decrease the interval I over which our test function is chosen to be equal to 1. By doing so, we narrowed down the interval in which we know that u double prime is equal to f bar. Can you see where this is going? We can decrease the interval even further, and in the limit we will see that we are very certain about where u double prime must take the value f bar. Let's step back for a second and see what we have achieved. By choosing a specifically designed test function, we found that u double prime equals f bar at one point x. Because the weak formulation must hold true for any test function, we can repeat the same argument to find that u double prime equals f bar at another point x. Let's see what happens if we repeat this argument a couple of times. We observe that for every test function that we choose, we find that u double prime equals f bar at one point x. And we can choose infinitely many of such test functions. Thus we will find that u double prime equals f bar at each point x. Do you remember this equation? We have recovered the original form of our differential equation. That is, we have derived the strong form from the weak form. Let's recap. Earlier in this video we have seen that we can derive the weak form from the strong form. And now we have seen that the strong form can be derived from the weak form. Thus, the strong form and the weak form are equivalent. Or to put it in other words, both formulations entail the same information about our unknown solution function u. This means that we can choose either of these formulations for the numerical analysis. As I already mentioned, the finite element method is one of the most powerful numerical methods. And it turns out that the weak form is much better suited for applying the finite element method than the strong form. But still, one important step is missing before we can apply the finite element method. Earlier in this video, we have seen that in the finite element method, we want to parameterize the solution using a linear combination of shape functions and unknown parameters ui. Using linear shape functions, we have observed that the second derivative of our parameterized ansatz is 0, no matter how we choose the unknown parameters in our ansatz. Therefore, we couldn't substitute the ansatz in the strong formulation to compute the unknown parameters ui. But we can see that we still have the same problem for the weak formulation, because the solution function u still appears with its second derivative in the weak formulation. And this is the reason why one important last transformation of the weak formulation is required. For this final transformation, we use the concept of partial integration. Recall that the formula for partial integration states that the integral from 0 to 1 of the derivative of a function u times a function v is equal to the product of u and v evaluated at x equals 1 minus the product of u and v evaluated at x equals 0 minus the integral of u times the derivative of v. To apply partial integration to our weak formulation, we have to slightly modify this formula. Note that the formula of partial integration must hold true for any function u. Therefore, we can substitute the function u in the formula by its derivative u prime. The resulting formula looks like this. We observe that the left-hand side of the partial integration formula is equivalent to the left-hand side of the weak form. Thus, we can substitute the right-hand side of the partial integration formula in the weak form. We can see that because of the boundary condition that states that u prime at x equals 1 is 0, one term in the weak form vanishes. The other boundary condition states that u at x equals 0 is 0. Now we can use a small trick. As the weak form must hold true for all test functions, we can freely decide how the test functions should look like. As we already know the value of u at x equals 0, we constrain the test functions to be 0 at this point. That is, we claim that the weak form must hold true for all test functions that are 0 at x equals 0. This trick further simplifies the expression for our weak formulation. Now we have finally rearranged the weak form such that it is well suited for numerical analysis. And we can see why applying partial integration was so useful. Until now, the second derivative of the solution function u was present in the weak form. But after applying partial integration, the highest derivative of u that appears in the weak form is u prime. At this point, we can finally realize why the strong form is called the strong form and the weak form is called the weak form. The strong formulation puts strong requirements on how the solution function u should look like. It requires u to be 2 times differentiable. The weak formulation puts weaker requirements on how the solution function u should look like. It requires u to be just once differentiable. Therefore, the weak form is much better suited for numerical analysis and in particular for the finite element analysis. In the scope of this video, we cannot take a deep dive into the finite element method. But a video about the weak formulation without touching the finite element method wouldn't feel right. Therefore, let's take a short look at the core ideas of the finite element method. To apply the finite element method, let's recap the parametric ansatz for the solution function. We assume that the solution can be expressed by a linear combination of unknown parameters ui and known shape functions n. Note that this is an approximation. With numerical methods like the finite element method, we do not intend to find the solution function u exactly, but a sufficiently good approximation of it. For linear shape functions, we get a piecewise linear ansatz for u. By tweaking the parameters ui, we obtain differently shaped functions u. Our goal is now to compute the unknown parameters ui. The first thing that we observe is that the boundary condition u at x equals 0 is 0 tells us that the first parameter u0 must be 0. And therefore our ansatz simplifies slightly. As the first derivative of u appears in the weak formulation, we have to differentiate the ansatz. This is not difficult because the parameters ui do not depend on x and only the shape functions depend on x. Therefore, the derivative of u is simply the sum of the parameters ui times the derivatives of the shape functions. Next, we simply substitute our ansatz in the weak formulation. Note that the integral of a sum of some functions is equal to the sum of the integrals of the functions. Therefore, we can switch the integral and the sum sign in our weak form. Expanding the sum, we obtain the following expression. Let's take a closer look at this expression. The unknown parameters ui do not depend on x. Therefore, they can be written outside the integrals. Let's carefully think about what this expression tells us. On the left-hand side, we have our unknown parameters ui, which are respectively multiplied by an integral of a shape function derivative and a test function derivative. On the right-hand side, we have the integral of f times the test function. Both the shape function derivatives and the function f are known. Therefore, all the integrals in our expression could be computed if a test function v was given. We also observed that if all the integrals in our expression could be computed, we would obtain a linear equation for our unknown parameters ui. This is an important result, because for any given test function v, we obtain a linear equation for our unknown parameters. We recall that the weak form must be fulfilled for any test function that is 0 at x equals 0. Thus, we can simply choose as many distinct test functions as we have unknown parameters. And for every of these chosen test functions, we obtain a linear equation. We have a lot of freedom on how to choose the test functions, but the most convenient choice is to choose the shape functions n as test functions. We finally arrive at 5 equations in which the integrals are computable because the integrands are known quantities. A fundamental advantage of the finite element method is that these integrals can be computed very efficiently. However, this goes beyond the scope of this video. Computing all integrals on the left-hand side and denoting the result by capital K, and computing all integrals on the right-hand side and denoting the results by capital F, leads to this compact representation of the system of equations. Because we have as many equations as unknowns, this system of equations can be solved for the unknown parameters ui. Let's plot the resulting solution for our specific example. Comparing the result to the analytical solution in yellow, we observe that the numerical and the analytical solution are quite similar. I hope you were able to develop some intuition about the weak formulation and the finite element method. At the end, I want to emphasize that there are some fairly important concepts that are not covered in this video. First, the concept of the weak formulation is closely related to the calculus of variations. Many weak formulations can be interpreted as the necessary condition for minimizing an energy functional. However, this is not always possible, and in physics or engineering classes, differential equations are typically introduced by deriving their strong formulation through physical arguments like, for example, the balance of linear momentum or the conservation of energy in form of heat. Therefore, I think that deriving the weak formulation from the strong formulation is slightly more accessible. Further, please keep in mind that this video did not intend to provide profound mathematical proofs, but rather some intuition about the concept of the weak formulation. For example, we have not taken a close look at the properties that the solution function and the test functions must fulfill in terms of differentiability and integrability. That is, we have not specified which function spaces these functions should belong to. This is a matter of study of functional analysis, a field of mathematics that is well suited to rigorously study differential equations and how they can be solved. Finally, in this video we left out many technical details about the finite element method, which would have gone beyond the scope of this video about the weak formulation. Most importantly, we have not discussed how to compute the integrals appearing in the parametrized version of the weak formulation, and we did not leave the one-dimensional setting. Let me know if you would be interested in any content of this kind. If you found this video useful, please consider sharing it with your friends. Thanks for staying till the end. Bye!